Okay, so thanks very much for that introduction, and thanks so much to the organizers for having me here. It's really been a great conference. So I'm going to talk about this topic, but I want to do a little bit of a detour first into something that's a little bit of a technical issue, but I think will be of great interest to a lot of people here at this conference in particular. So the work I'm going to show you is data collected with Neuropixel's electrode arrays. So you've heard about these at previous ICANs if you were here. This is the device itself. And a Neuropixel's array, which is published and is an effort led by Tim Harris at the Geneva Research Campus. The Neuropixel's array is sort of special because it incorporates on a single CMOS fabricated device both the recording shank that goes into the brain and has 1,000 recording sites, of which 400 are selectable at any one time, along with, at the base, the entire recording system, the amplifiers, digitizers, and multiplexers to pre-process all of the data on chip. And that allows you to sort of efficiently get the data off of the probe and also keep noise levels low and other things. So this is a device actually that I think is a new concept to many people in the field. It was to me. Actually, I was recently learning about the work that they did here, Ken and Khalil Najafi in the 80s, pioneering this kind of concept of putting active electronics on the probe. So that actually concept really came from University of Michigan, and it's fun to be here and talk about this work. So the NeuroPixel's probes have what we refer to, I think, in this paper as high-density recording sites, which is recording sites spaced in this sort of dense tetrode, sort of continuous tetrode-like arrangement all the way up the shank of the probe. And if you record in the brain, here's an example set of waveforms from a neuron, in this case a CA1 pyramidal neuron. And you can see that this waveform from this one individual neuron is observed on many adjacent recording sites. And if we sort of zoom in and look at the spacing here, that's 20 microns sort of row to row along the shank. And so this individual neuron is observed over really hundreds of microns. And for a neuron like this, it's clear that the sampling density on these probes is more than sufficient to really capture the spikes of this neuron and allow you to spike sort them very well, because you have a lot of information about every individual action potential. And this is consistent with classic modeling work, which again looked at these CA1 pyramidal neurons, and on the same sort of spatial scale showed that it was indeed expected that you should be able to observe these neurons over sort of hundreds of microns type scale. But CA1 pyramidal neurons are really going to be about as big as it gets in terms of electrical fields, at least in a mouse brain. They both have very large neurons and also very polarized morphologies, which lead to these sort of broad electrical fields. So we can expect that it will only be smaller from there. Any other type of neuron is going to have smaller and possibly smaller electrical fields. And if we wanted to try to predict just how small those electrical fields might be, it would be really a challenge. This paper, these models that generated these data, not only involved all the sort of detailed morphological information of the neurons that you can see there, but also involved 12 different kinds of active conductances in the neurons. And we just really don't have data about all the different types of neurons across the brain, what kinds of active conductances they have, even what kinds of morphologies they have at this level of detail. And even with all of that, this model was still sort of predicting very well the observed extracellular signatures, but also still missing some things. So ultimately, the only way to figure out what kinds of neuron shapes that we need to be trying to record with an electrode and trying to answer this question of how dense should an electrode array be is to go measure the shapes of these extracellular fields. So I am excited to tell you today about some data that was collected with a special probe that the NeuroSeeker Project, which is sort of a parallel project to the NeuroPixels project, also based in Europe and also involving IMEC, the company in Belgium that makes the NeuroPixels probes. So in this project, thanks to the NeuroSeeker Project, they developed a probe that was designed to answer this question of how dense the electrode array should be, how small are the electric fields of the neurons. And this probe has an extraordinarily dense arrangement, so Adam's term for it is ultra dense, that's the term I'll use, where there's 6 micron pitch between sites, and the sites are 5 by 5 microns. And just to show really how dense this is, here I'm overlaying the red squares indicate the recording sites on this particular probe, and the gray squares are these high-density sites on the NeuroPixels probe. And so in comparison to this probe, the NeuroPixels probe really looks like not high-density, which I think is amusing, maybe. And Adam, and specifically Joanna Nato in Adam's lab, used this probe to record many different sites in 5 brain regions: cortex, cerebellum, hippocampus, thalamus, and striatum, in anesthetized rats. So what kinds of waveforms are observed across the brain? So here's an example. So I have a couple of different representations of the same waveform here. So on the left is just the mean waveform of this neuron as it was observed on many different recording sites. And you can see that this neuron had a large waveform on lots of recording sites and a small waveform then as you got further away from the presumed center of the neuron, or the soma of the neuron. Here, on the right, we're abstracting just the amplitude, sort of peak to trough amplitude on each channel as a color map. And you can see the peak amplitude is about 130 microvolts, and then there's a sort of considerable expanse where the amplitude is high enough to see it well on each site. And you can sort of tell, so this color map overlays this red square, and you can tell that if you overlay this here, as we expect from the kind of neurons that I showed, neurons like the example one that I showed you, you would see this neuron on multiple NeuroPixel sites, and for a neuron like this, the NeuroPixel's density is clearly high enough. In this middle one, I'm just sort of amplifying some of the lower amplitude sites so that you can see their shapes better. Okay, but we also see much smaller waveforms. So here's a neuron that exists really only on a few sites. So even from the peak site to the neighboring sites, just 6 microns apart, this neuron already goes to sort of nearly undetectable amplitude. And the spatial extent of this neuron's waveform clearly falls even in between the gaps of the NeuroPixel sites. So not only would you be missing these kinds of neurons in between those gaps often, but if there's any movement of the probe relative to the brain, or movement of the brain relative to the probe, then that neuron could easily become undetectable in a way that the CA1 pyramidal neuron wouldn't. Yeah, Yuri? Yeah.
It looks triphasic and very short. Could it be an axon?
I don't know the answer to that question, but I agree with you that there are interesting features of these waveforms. Yeah, Michael?
I just missed it, but is this tissue culture, or how is this?
It's a urethane anesthetized rat.
Okay, so the
In vivo, yeah.
inserted into the brain.
Exactly, yeah. So there's a couple of different, they're showing on this graphic a couple of the different recording site locations. It's not, I don't have the histology here, but you get the basic idea. They just stuck it in a few different places. So this is in neocortex. Okay, and we may have expected actually from the NeuroPixels recordings that we would see some neurons like this, because I have sort of isolated examples where I did find such a neuron where on a NeuroPixel site, one site can see it really with large amplitude, but adjacent sites already don't see anything about that neuron. And so we might have expected that there are these neurons with really, really small electrical fields. And I think the other exciting thing about these data is they're really revealing some maybe interesting properties of some of these electrical fields that we really can't even see with the NeuroPixels, where, for instance, here there's both downward going and upward going action potentials in close apposition, presumably reflecting current sources and sinks and sources related to different parts of the neuron's morphology. Okay, so, and then one other thing I wanted to say was that these kind of very small neurons, we see them in the data from all of the brain regions that we recorded from. It's not just cortical neurons, but also hippocampal, thalamic, striatal, and cerebellar neurons. Okay, so the summary of this part of the talk, before I then actually talk about the neural basis of behavior, is that we observed these neurons with about 10 micron scale electrical fields across the brain. So these kinds of neurons are going to be disproportionately missed. There will be a sampling bias against these kinds of neurons, even with an electrode with high density like NeuroPixels. And I think this could potentially give partial explanation for this sort of dark matter problem in neuroscience that some people have talked about, that you don't observe spikes from as many neurons as you think you should based on geometrical considerations. And then the last conclusion is that these, as I mentioned, these neurons will be impossible to drift correct without higher density electrode arrays. So you'll just, if there's any movement, you won't be able to continue to see this neuron. The neuron will just disappear from sight, and you'll lose the spikes of that neuron when there's drift of the brain relative to the probe. So I think this really raises a challenge for the field in terms of designing electrode arrays, and suggests that this sort of 6 micron pitch may be a good scale to aim for. It's possible that we even need to go more dense, I don't know. But I think these data are really interesting from that perspective. Okay, so now I'm going to talk about behavior. So I've taken up all my time for introduction, so I'll be really brief. But the question the big picture question that we want to answer is what brain regions are involved in generating a behavior with what roles and when. And the idea here is that we were thinking about how a behavior works. And I'll tell you about the particular behavior that we've trained in mice in just a second. And what's known about the literature. People think different cortical areas are involved. People think different parts of striatum are involved, et cetera. Really, the problem is, or the sort of big picture problem that I think we're interested in, is every neuron in the brain is just a few synapses away from any other neuron in the brain. Almost every region connects to every other region. All of these systems are recurrently interconnected with each other. And unless we look, we're not going to be able to predict or know what signals are getting distributed to which parts of the brain, and which parts of the brain therefore might be playing a role in doing any particular behavioral task. So the behavioral task that we're studying is a behavioral task in mice. Wait, can I use that? And in this task, we surround mice with 3 computer screens, here sort of viewed from above, on which we'll show visual stimuli. We give the mice a wheel that they rest their forepaws on and can turn left and right to indicate their choices, their perception of the visual stimuli, according to a rule that I'll describe in a moment. We reward the mice for correct choices with water rewards, and the mice are head fixed during this task so that we can combine it with NeuroPixel's recordings. So what do the mice see on the screen, and what are they supposed to do with that wheel? So if they see a stimulus, so they'll see stimuli like this, and if they see a stimulus on the left, they should spin the wheel clockwise. When they spin the wheel, the stimulus is actually going to move with the wheel. It's a sort of closed loop type thing, where another way to say their goal is to spin the wheel such that that stimulus moves into the central screen. And so therefore, if the stimulus appears on the right, then they should spin the wheel the opposite direction, counterclockwise, with the same goal of bringing that stimulus into the center of the screen. And there's a third type of trial in which no stimulus is presented, and they should hold the wheel still for 1.5 seconds. So this task is what we call a perceptual decision-making task, in that they've got to make a perceptual discrimination about some stimuli they're presented with and decide which action to perform on the basis of it. And we think that this task is very much like many behaviors that humans do. It's sort of a thing that the mammalian brain is set up to do. Take arbitrary stimuli and make response associations with them. You could think about, for instance, driving your car and seeing a red light or a green light, meaning indicating different actions that you should take. So I think these kind of behaviors are sort of ubiquitous for mammals. Here's a video of the mouse performing this task, and I'm going to cover up the brain on this mouse because it's irrelevant for what I want to show you. But what you're going to see is the screen that the mouse sees down here, and then you can just about see the wheel that the mouse has its forepaws on here. And so the stimuli appear, and then the mouse turns the wheel. And you'll notice there's no particular delay period in this task. The mouse can execute the behavior as soon as the stimuli come up. So we're not studying working memory, we're just studying the process of generating the behavior in response to the stimulus.
Nick, can I ask how long is it taking to train?
Some of them will learn the basic version of the task, just turn one way for the stimulus on the right and the other way for the stimulus on the left. Even in just a few sessions, on average, it's more like 2 to 4 weeks for mice. Yeah. Okay, so we trained mice in this task, and then we recorded with NeuroPixel's arrays in many parts of the brain. So we recorded acutely. We would do craniotomies and insert probes just for the duration of the recording session, and then remove the probes and record from a different place the next day. And what I want you to see, so each one of these represents the 4 millimeter long recording span of the NeuroPixel's probe on a particular recording trajectory for a particular session, and registered to the Allen Brain Atlas. And what I want you to see is just that even in a small number of mice and in a reasonable number of recording sessions, we are able to cover really a significant fraction of the total volume of the mouse brain with these recordings. So what do these recordings look like? So I'll show you an example recording. In this one, I inserted 2 electrodes simultaneously, one through visual cortex, part of the hippocampal formation, and down into thalamus, and the other along the bank of frontal cortex through sort of secondary motor cortex, cingulate, prelimbic, infralimbic, and some olfactory related structures below. And these are the data. So here again is the mouse sort of performing the task, and these are the sort of real-time data that are going on in these different brain regions in frontal cortex, visual cortex, hippocampus, and thalamus, all simultaneously. And obviously there's a lot of complicated stuff going on, but you can see at a glance that there's a lot of dynamics. The dynamics are different across areas, and all areas have some relationship to task activity to some extent. Okay, so let's then look more closely. So the question is, what task correlates do we see in which brain regions? So in here, I'm going to show you just an example neuron to get started. So this neuron was recorded in the deep layers of primary visual cortex. This is the waveform as seen on the NeuroPixels probes. And this is some task-related activity. So aligned to visual stimulus onset at time 0 here, and sorted, in this case, the rasters by the contrast of the stimulus from high contrast, medium, low, and 0 contrast stimulus. This neuron had robust responses in a contrast-dependent way aligned to the visual stimulus onset. So this is the kind of response you might expect from a visual cortex neuron. And indeed, if I average across all of the primary visual cortex neurons, we can see that on average, the spiking activity in visual cortex responds robustly after visual stimulus onset. And now I'm going to do the same kind of analysis of looking at individual neurons, PSDHs, and then just averaging across neurons. It's the sort of simplest and most basic analysis you could think to do in other brain regions. So after primary visual cortex, we see activity in secondary visual cortex. That activity then arises in secondary motor cortex in the front, and finally in primary motor cortex just posterior to the secondary motor cortex. And so you can see that there's a progression of task-related activity, a sort of a sequence at a global scale across cortical areas in this task. But with the NeuroPixels probes, we weren't just recording from cortex, we were also recording from subcortical structures. And the first structure to respond that we observed aligned to the visual stimulus onset was actually not the primary visual cortex, but the superficial layers of the superior colliculus. This structure receives direct retinal input, and so it's not surprising that it's responding more rapidly than V1. Here in the middle of this sequence is the catoputamen, that's the striatum, the input region of the basal ganglia. It's responding after primary and secondary visual cortex, but before the motor cortices. And then finally, I put another area on here, the midbrain reticular nucleus, which is a deep midbrain structure below the superior colliculus, which is responding after secondary motor cortex and striatum, but before primary motor cortex. And I'll come back to this structure in just a minute. So looking across the brain, we can see that task-related activity is flowing through many structures, not just the ones I've highlighted before. So here I'm showing that same data from the previous slide as a color map. So each row is one area, and the labels of the areas are over here. And here I'm sort of grouping them into large-scale categories: basal ganglia areas, frontal cortex areas, midbrain areas, etc. And so you can see that this task-related activity is flowing through all of these areas. All of these areas really are responding in some way to the task. So in particular, they respond in a couple of key ways. So reward-related activity appears to be global. So now I'm again showing just the average spiking response of neurons in all of these brain regions, but aligned to the reward delivery. So the time at the end of the trial when the mouse gets a reward if the mouse performed the trial successfully. And you can see that nearly every region is responding with short latency, less than 50 milliseconds after the delivery of the reward. So what is actually happening here? When we deliver a reward, we open a valve to allow some water to flow down that tube that I showed you to the mouse so that he can lick it. And the valve opening makes a clicking sound. And so this is an auditory stimulus that perfectly predicts that the reward, and the mouse has learned over weeks that this stimulus is predicting that a reward has been delivered. And so this is an auditory response that's reward predictive, but we think this response is not just an auditory response, because there's another auditory stimulus in the task, which is a beep that's a sort of go cue And if we align activity to the beep onset, you can see that whereas some of the structures respond similarly to the beep, for instance, this is the medial geniculate nucleus of the thalamus, the part of the thalamus that processes auditory stimuli, and that area responds relatively identically. Most of the areas do not also respond to the beep. And so this is not just an auditory response, but rather a reward-specific response. In addition to reward, action-related activity is also observed globally. So here I'm aligning to the movement onset, the time when the mouse starts pushing the wheel and making his response. And you can see that in the sort of 50 to 100 milliseconds prior to movement onset, nearly every brain region is ramping up its activity prior to movement onset. So at least areas are getting a signal, perhaps a corollary discharge signal, or perhaps they're playing some active role in the movement generation, but at least every area is as representing the fact that a movement is impending. So the key aspect of this task, though, is the choice, right? The mouse sees a stimulus, he's got to make a decision about it. So where do we find neurons that can predict the choice? So here's a neuron from secondary motor cortex, which ramps up its activity prior to movement onset. So this is time 0, just like in the last plot, is movement onset. And it ramps up a little faster into a higher level for rightward choice trials than leftward choice trials. And about 50 milliseconds before the choice, you could discriminate with some success from the activity of this neuron which choice the mouse was about to make. And so given the existence of these neurons, we might suggest that the cortex, the secondary motor cortex, might be involved in generating and driving the choice of the mouse in this behavior. Let me skip this slide. However, we also recorded these subcortical structures. And so now I'm coming back to the midbrain reticular nucleus. In this structure, we found neurons like this one, where they not only encode the choice of the mouse much more strongly than the neurons in cortex, but also earlier. So this neuron, you can see, discriminates between leftward and rightward choices about 100 milliseconds or more before the choice onset. And to quantify this, we fit a very simple model to the spiking activity, which is just a linear regression that has terms for the contrast of the stimuli and the decision. You could think of this as a way of looking at error trials, because we're using the fact that sometimes for given contrast conditions, the mouse will make one decision, and other times will make the other decision, that is, make an error, to discriminate the parts of the neural activity that are dependent on the decision and on the contrast. And if we look at the decision term, so how much of the neuron's activity can be explained by this last regression term, what we find is that that regression term is important for explaining the activity in the midbrain reticular nucleus and the deep layers of the superior colliculus, these midbrain structures, significantly earlier than in secondary motor cortex and in striatum. And so this does not prove that these deep areas make the decision, because of course there could be somewhere upstream of these neurons that's making the decision that we haven't recorded. But it does suggest that the neurons we've recorded in secondary motor cortex and striatum are too late to be involved in the decision process, because at least in the midbrain, the decisions are already reflected before those neurons even come to represent the decision. So to summarize, with the NeuroPixel probes, we were able to record many thousands of neurons across the mouse brain during a behavioral task. Activity is observed in many regions simultaneously, and specifically motor and reward-related signals appear to be global. Whereas choice predictive signals are rare, and we observed those earliest in the midbrain, which was a surprise to us, and we think suggests a lot of further questions for the neural basis of perceptual decision-making. So I'm going to briefly thank especially Tim Harris and the NeuroPixels Consortium for these probes, and Kenneth and Matteo, my advisors in this work. I'm happy to take any questions.